Right, so when you're doing a Ferris wheel problem, if you were guessing and you guess that Ferris wheels aren't going that fast, and look, it says it's doing one revolution in 7 seconds. That's sort of a lot of time to do one revolution. It's not like I'm doing 7 revolutions in 1 second. I'm sure if I were doing 7 revolutions in 1 second, I better have a seatbelt on because I'm going to go flying off the ride. But one revolution in 7 seconds, probably that's slow enough that when I'm at the top, I'm not coming off the ride. So again, it would probably depend also on the size of the Ferris wheel because, what size circle am I moving through in 7 seconds? So I'm going to, when I put my forces on this, it says find the apparent weight of the person at the highest point. So what I would do is, first of all, my weight will always be down. So my weight is going to be in this direction. But because it is a Ferris wheel, I'm going to assume that the normal force is up. So I'm going to label that the weight, and I'm going to label that the normal force. And whenever you do these problems, one thing I do know is that that arrow needs to be bigger than that because it's changing direction. So I need a net force towards the center of the circle in order to change direction. If I didn't have that, and if at this point there were no forces on the object, it would move in a straight line. So it's continually changing direction. Now, when you did this problem out for homework, maybe you had the normal force down because tension is always down at the top. No problem, just leave it down, but your answer then, if I'm correct that we don't need a seatbelt at the top, then my answer is going to come out positive, and your answer is going to come out negative. We're both right. As long as I look at your picture and see that your picture matches the correct direction. So that's the way I would have it. So if I sum up my forces, I'm going to have W, because W is towards the center of the circle. Fn is away from the center of the circle, and it's going to equal mv squared over r, or mr omega squared. Since the r is not the unknown in the problem, I'm going to use mv squared over r. So there's my descriptive equation. Now the unknown, the apparent weight, that's your normal force. So if I rearrange this equation to solve for the normal force, I'd be moving that on this side and that on the other side. So my result is going to be that the normal force is going to equal W. And actually, I'm looking at the problem, and they don't give me W. They're giving me the mass. So I'm going to replace W also. What will I replace W with? mg. So I'm going to write that as mg minus mv squared over r. Be careful when you're moving things around, because I'll have people who get this right, and then somehow they move it around and they'll end up having mv squared over r minus mg. Like they just mess up somewhere in moving things around. Now, the next thing I would do is just do a checklist. What do I know? I do know the mass in the problem. The mass is 112 kilograms. I know the radius, so I know that. I know g because it's a constant. So the only thing I don't know directly is v, but I can get it from the fact that it takes 7 seconds to make one revolution. So I do need to, on the side, figure out what v is. So I'm going to do that v is if it does one revolution in 7 seconds, I can convert that into meters per second in one step. So I'm going to go from revolutions to meters. One revolution, I move through the circumference of the circle. So it's going to be 2 pi, and the radius is 8.2 meters. And if you solve that, what does that work out to be? 51.5? Okay, 51.5. That doesn't sound right. I mean, I'm looking at the numbers here, and that's just a little, this number right here is going to be like 6 point something times a little bit more than 1. 7.36? Okay, 7.36 meters per second. All right, so that's the V. Do you know what the mistake was? Or oh, all right. So then with that answer, I want the apparent weight. So this is, again, this is the answer for part A. So it's going to equal mg minus mv squared divided by r. So for the mass, we're going to put in 112 kilograms. For g, that's a constant, 9.8 meters per second squared. The v is 7.36 meters per second. And the r is 8.2 meters. So that will equal the apparent weight at the highest point. And that answer, did it come out to 358? With those numbers, 358. The good thing is, once we've done part A, like that's the high point. If we do the low point, the equation's just going to be a little, or even the midpoint, the equation's just going to be a little bit different. But we're not going to have to resolve for V if they're asking for the lowest point or the midpoint. We don't have to do that again. We've already done it. So that's your answer for part A. So in part B, it says find the apparent weight of the person at the midpoint. So I'll do this in a different color. So the midpoint, I'm going to have that the weight is straight down. It's going to be the same magnitude as what it was there. So that's going to be, so the weight is going to be straight down. But I now need a net result towards the center of the circle. So I'm going to have the normal force. So there's going to be something there. I don't know whether it's the back of the seat or some part of the seat belt. There's something that has to be changing the direction because my weight is not in any way helping me change direction. My weight would actually be a tangential force. So this would be the normal force for part B. So my equation is going to simply be, if I sum up my centripetal forces, so this is for part B, the only thing I have is Fn. So Fn equals mv squared over r. So the weight isn't involved in it at all because it's perpendicular to that. So just plug in the numbers and you'll have the answer. So for part B, Fn equals mv squared divided by r. So the m is 112 kilograms. The v is 7.36 meters per second, and the r is 8.2 meters. And if you solve that now, whatever the number, now it's 358 there, it would be a lot more down there because you'd be pushed into the seat. If you know, the weight would be working against you, and the midpoint should be halfway in between. So I hope that you get the answer for this. I think I gave you, what, 740? Was it 740? So if this is 740, without even doing the lowest point, because they didn't ask for the lowest point, but I could do the lowest point where whatever the difference is between this and this, if I now add it there, I'm going to get what the normal force would be down there. So 740 minus 358. What's 740 minus 358? Someone do that on their calculator. It's going to be like 3 something. What is it? 382. Take 382 and add it to 740 now. So add 740 to 382. 1,122. That would actually be the normal force at the bottom. Everyone follow that? Because, you know, if it's 358 there and 740 there, then it's going to be that, you know, this number has to be halfway between those two numbers. So that would be the answer if they had asked for the low point. Now, in part C, now part C is the part that on the test, that's the one that people get wrong, that they mess up. So it says, what would be the angular velocity if its apparent weight at the highest point was 0? So the equation doesn't change. We're just going to now, we're going to make the normal force 0. So I'll do this in another color. So if I made, here's my picture at the high point. If I make that 0, so if the apparent weight at the highest point was 0, then I have to move at a different speed. At this speed, I'm going to have that normal force. So I'm now going to change my speed. You know, what would the speed be for the apparent weight at the high point to be 0? So my equation is going to be, if I sum up my centripetal forces, so here's part C, it's going to be W equals mv squared over r. That would be the equation if we eliminate the normal force from this equation. Then it's just going to be W equals mv squared over r. So I know W is mg, so I get mg equals mv squared over r. The advantage of doing that is I can cancel out the mass. And if I rearrange this equation to solve for v, all I have to do is move the r up there and take the square root. So my equation is going to be, for part C, v equals the square root of rg. So that's my equation for part C. And so just put in the numbers. We're going to have the r is 8.2 meters. And the g is 9.8 meters per second squared. Now you might be saying, why are we solving for v? They asked me for the angular velocity. But once I get that answer, I'm just going to convert it into an angular velocity. Because v, omega, and t, you can go between one and the other. So my guess is the answer for this is somewhere between 8.2 and 9.8. So what's that? 8.96. So 8.96 meters per second. And since they wanted the angular velocity actually in revolutions per second, then all I have to do is go omega. I'm going to start with 8.96 meters per second. And in one step, I can get that in revs per second. So I'm just going to go from meters to revs. 1 rev is 2 pi times the radius here is 8.2 meters. And you can see here that my meter will cancel out with my meter, and my answer will be in revs per second, and it will be an angular velocity. Any angle divided by a time is an angular velocity. So radians per second, revolutions per minute, degrees per second, even, you know, because degree is a unit, is an angular unit. Any of those is an angular velocity. And what do you get for that answer? 0.174? 0.174 revs per second.